Hello dear students, welcome to the lecture 3 of Security of Information Systems. So today's topic is,
Cryptography.
yes, okay. So our outline of this lecture.
What is cryptography? Brief crypto history. Security issues. Symmetric cryptography, stream ciphers, block ciphers, hash functions. Asymmetric cryptography, factoring-based mechanisms. Discrete logarithms, digital signatures. Quantum-resistant crypto. Want to learn more? Look up Unique 4220.
Okay, I'm not sure what is this. Okay, I guess this is related to language of the professor. Okay,
The security pyramid.
so in the security pyramid there is user, secure systems, communication protocols,
Cryptographic mechanisms.
and below that mathematics, electronics, statistics, informatics, quantum physics, ethics, and politics. Okay,
What is cryptology?
so Alice wants to communicate with Bob over a secure communication. Okay, or let's say over unsecure channels with secure communication. And there is Oscar who wants to uh, see what they are talking. Okay. So what options do Alice have? Alice can have,
Symmetric crypto, asymmetric crypto.
and what do we need for this?
Confidentiality, integrity, authenticity, non-repudiation.
Okay, so the terminology is,
Cryptology,
and it is branched into.
cryptography, cryptanalysis.
Okay, so let's learn about them.
Cryptography is the science of secret writing with the goal of hiding the meaning of a message.
And
Cryptanalysis is the science and sometimes art of breaking cryptosystems.
so with cryptography, you want to hide something from third parties so they cannot see it, and from cryptanalysis, the third parties want to break into the cryptography systems of other people or other systems.
Model of symmetric cryptosystem.
So Alice uses an encryptor with the help of a key source, and uh, it generates a secure channel and sends her message to the Bob, and Bob uses a decryptor and receives the message. So meanwhile, the persons or systems that are not in this secure channel cannot read the Alice's message or the content. Okay, so in this case it is being Oscar. Oscar cannot decrypt the message and see the content of that message. Okay, so there are the cryptography has been used since the ages. So one of the four first examples is Caesar cipher.
Caesar cipher.
So Caesar has ciphered the alphabet as like this. So the plain text this becomes this in the Caesar cipher. If you don't know the ciphered alphabet, it would be hard or impossible for you to decrypt it. Okay. So let's learn more information about Caesar cipher. In this lecture, I will be able to provide only little information from the slides. However, for each topic we need to check Google to find more information because it's impossible to put all of them into a slide. Okay, Caesar cipher.
In cryptography, a Caesar cipher, also known as Caesar's cipher, the shift cipher, Caesar's code or Caesar shift, is one of the simplest and most widely known encryption techniques. It is a type of substitution cipher in which each letter in the plaintext is replaced by a letter some fixed number of positions down the alphabet. For example, with a left shift of 3, D would be replaced by A, E would become B, and so on. The method is named after Julius Caesar, who used it in his private correspondence. The encryption step performed by a Caesar cipher is often incorporated as part of more complex schemes, such as the Vigenère cipher, and still has modern application in the ROT13 system. As with all single alphabet substitution ciphers, the Caesar cipher is easily broken and in modern practice offers essentially no communication security.
Yeah, currently, of course, this would provide zero security. It could be decrypted easily with strong computers. So to get the idea of ciphering, let's check this easy example.
The transformation can be represented by aligning two alphabets. The cipher alphabet is the plain alphabet rotated left or right by some number of positions. For instance, here is a Caesar cipher using a left rotation of 3 places, equivalent to a right shift of 23. The shift parameter is used as the key.
So when, let's read it.
When encrypting, a person looks up each letter of the message in the plain line and writes down the corresponding letter in the cipher line.
Okay.
The quick brown fox jumps over the lazy dog.
And the cipher text becomes this. Let's see how the AI reads it.
QEBNRFZHYOLTKCLUGRJMPLSBOQEBIXWVALD.
So the deciphering is done in reverse.
Deciphering is done in reverse, with a right shift of 3. The encryption can also be represented using modular arithmetic by first transforming the letters into numbers, according to the scheme: A right pointing arrow 0, B right pointing arrow 1, Z right pointing arrow 25. 2. Encryption of a letter X by a shift N can be described mathematically as 3.
So decryption is performed similarly. And so the letter T becomes Q. And when we are deciphering, we will just look the cipher letter, alphabet, and when we see the Q, we will just type the T. So it is the reverse of the cipher operation. And this is one of the basic ciphering. And there is history and usage. Okay, so Caesar said this.
If he had anything confidential to say, he wrote it in cipher, that is, by so changing the order of the letters of the alphabet, that not a word could be made out. If anyone wishes to decipher these, and get at their meaning, he must substitute the fourth letter of the alphabet, namely D, for A, and so with the others.
Okay, so you can learn more information about this. Let's continue. An example here. Okay. So numerical encoding of the alphabet.
Using this encoding, many classical crypto systems can be expressed as algebraic functions over Z26 English alphabet or Z29 Norwegian alphabet.
We use this technique for many things. For example, in machine learning, in artificial intelligence, to represent, let's say, categorical data set as features, we may encode them with integers, and therefore our algorithms may work better with integers. Okay. Encoding is used in many cases of computer science, in software engineering. So shift cipher, and let's look for shift cipher. Okay, so the shift cipher is basically uh, shifting methodology, and one of the example is Caesar cipher. There can be exhaustive search to decrypt the shift cipher. And how do we do that? Let's say we are shifting each key one by one, and this is the first shifting, this is the second shifting, third shifting, fourth shifting. And when we reach the 10th shifting, you see we are obtaining a logical sentence. I wonder if let's, yeah, okay, it fixes it. And now I can read it.
Cryptography is needed for secure communications.
So with just shifting each letter one by one, we have decrypted the shift cipher. It is so easy. Okay, it just took 10 steps. And there is also substitution cipher. Okay, with substitution cipher, the key space is much bigger.
Substitution cipher, example.
So let's look at a better example.
Hiding some data is known as encryption. When plain text is encrypted, it becomes unreadable and is known as ciphertext. In a substitution cipher, any character of plain text from the given fixed set of characters is substituted by some other character from the same set depending on a key. For example, with a shift of 1, A would be replaced by B, B would become C, and so on. Note, special case of substitution cipher is known as Caesar cipher, where the key is taken as 3.
Okay. You can also compose a custom substitution cipher. Let's say you can represent W as Q and represent L as U, and it would make the things much more complex. Okay. I'm looking for a good example. Okay, there's a good example.
The ciphertext alphabet is sometimes different from the plaintext alphabet. For example, in the Pigpen cipher, the ciphertext consists of a set of symbols derived from a grid.
So when you
For
see
example,
So when you see this kind of sentence, you get no idea what they mean. And if you have the cipher alphabet, you can decrypt it. Okay.
although the number of possible keys is very large, 26, approximately equals 288.4, or about 88 bits, this cipher is not very strong, and is easily broken. Provided the message is of reasonable length, see below, the cryptanalyst can deduce the probable meaning of the most common symbols by analyzing the frequency distribution of the ciphertext. This allows formation of partial words, which can be tentatively filled in, progressively expanding the partial solution. See frequency analysis for a demonstration of this. In some cases, underlying words can also be determined from the pattern of their letters. For example, attract, osseous, and words with those two as the root are the only common English words with the pattern ABBCADB. Many people solve such ciphers for recreation, as with cryptogram puzzles in the newspaper. According to the Unicity distance of English, 27.6 letters of ciphertext are required to crack a mixed alphabet simple substitution. In practice, typically about 50 letters are needed, although some messages can be broken with fewer if unusual patterns are found. In other cases, the plaintext can be contrived to have a nearly flat frequency distribution, and much longer plaintexts will then be required by the cryptanalyst.
So we can set any alphabet to any any letter as we want. It would have about 26 factor alphabet possibilities. However, since they will be actually words, they can be decoded easily with cryptanalysis. Okay, so this is not a strong way of security. Lessons learned.
A cipher with a small keyspace can easily be attacked by exhaustive search. A large keyspace is necessary for a secure cipher, but it is by itself not sufficient. Mono-alphabetical substitution ciphers can easily be broken. Enigma. German WW2 crypto machine. Many different variants. Polyalphabetical substitution. Analyzed by Polish and English mathematicians.
So this is the Enigma K-list. And let's see some more information related to this. I think I will get more information about Enigma. Okay, there's Wikipedia page. Let's read some history about this.
Cryptanalysis of the Enigma ciphering system enabled the Western Allies in World War II to read substantial amounts of Morse-coded radio communications of the Axis powers that had been enciphered using Enigma machines. This yielded military intelligence which, along with that from other decrypted Axis radio and teleprinter transmissions, was given the codename Ultra. This was considered by Western Supreme Allied Commander Dwight D. Eisenhower to have been decisive to Allied victory. 1. The Enigma machines were a family of portable cipher machines with rotor scramblers. 2. Good operating procedures, properly enforced, would have made the plugboard Enigma machine unbreakable. 3, 4, 5. However, most of the German military forces, secret services, and civilian agencies that used Enigma employed poor operating procedures, and it was these poor procedures that allowed the Enigma machines to be reverse-engineered and the ciphers to be read. The German plugboard-equipped Enigma became Nazi Germany's principal crypto system. It was broken by the Polish General Staff's Cipher Bureau in December 1932, with the aid of French-supplied intelligence material obtained from a German spy. A month before the outbreak of World War II, at a conference held near Warsaw, the Polish Cipher Bureau shared its Enigma breaking techniques and technology with the French and British. During the German invasion of Poland, core Polish cipher bureau personnel were evacuated via Romania to France, where they established the PC Bruno Signals Intelligence Station with French facilities support. Successful cooperation among the Poles, the French, and the British at Bletchley Park continued until June 1940, when France surrendered to the Germans.
Okay, general principles. You see it has rotors, lamp port, a series of the rotors from an Enigma machine scrambler. Okay. Okay, this is a pretty advanced technology for that year. Okay, let's read these ones.
The strength of the security of the ciphers that were produced by the Enigma machine was a product of the large numbers associated with the scrambling process. It produced a polyalphabetic substitution cipher with a period 16,900 that was many times the length of the longest message. The three-rotor scrambler could be set in 26 times 26 times 26 equals 17, 576 ways, and the four-rotor scrambler in 26 times 17,576 equals 456,976 ways. With L leads on the plugboard, the number of ways that pairs of letters could be interchanged was 26. 26 2L times L times 2L with L equals 6, the number of combinations was 100,391,791,500, 100 billion, 16, and with 10 leads, it was 150,738,274,937,250, 151 trillion, 17.
So it was impossible to guess this number of combinations. However, what happened?
However, the way that Enigma was used by the Germans meant that, if the settings for one day or whatever period was represented by each row of the setting sheet were established, the rest of the messages for that network on that day could quickly be deciphered. The security of Enigma ciphers did have fundamental weaknesses that proved helpful to cryptanalysts. A letter could never be encrypted to itself, a consequence of the reflector. 19. This property was of great help in using cribs, short sections of plaintext thought to be somewhere in the ciphertext, and could be used to eliminate a crib in a particular position. For a possible location, if any letter in the crib matched a letter in the ciphertext at the same position, the location could be ruled out. 20. It was this feature that the British mathematician and logician Alan Turing exploited in designing the British Bombay. The plugboard connections were reciprocal, so that if A was plugged to N, then N likewise became A. It was this property that led mathematician Gordon Welchman at Bletchley Park to propose that a diagonal board be introduced into the Bombay, substantially reducing the number of incorrect rotor settings that the bombs found. The notches in the alphabet rings of rotors I to V were in different positions, which helped cryptanalysts to work out the wheel order by observing when the middle rotor was turned over by the right-hand rotor. There were substantial weaknesses, in both policies and practice, in the way that Enigma was used.
You see there is a lot of more information. However, it was broken. Maybe there is some more. How many?
Turing played a key role in this, inventing, along with fellow code breaker Gordon Welchman, a machine known as the Bombay. This device helped to significantly reduce the work of the code breakers. From mid-1940, German Air Force signals were being read at Bletchley and the intelligence gained from them was helping the war effort.
Yeah, I think. So this is probably a long history again. This is not so easy to explain here. However, if you wonder how they broken the Enigma, you can look for more information. Okay,
Cryptanalysis, attacking cryptosystems.
so what does crypto analysis mean? Classical cryptanalysis, implementation attacks, social engineering. Social engineering is very famous at the moment because it is almost impossible to crack properly coded systems, properly coded softwares. So the human part of the systems is the weakest part. So social engineering works much better than trying to figure out passwords or trying to find bugs, exploits, and such. Okay. So classical cryptanalysis requires mathematical analysis and brute force attacks. And with brute force attacks, it is almost impossible to crack any properly designed system. And implementation attacks, probably this is related to. Okay, it is explained here. Let's read them.
Classical attacks, mathematical analysis, brute force attack. Implementation attack, try to extract the key through reverse engineering or power measurement, e.g., for a banking smart card. Social engineering, e.g., trick a user into giving up her password.
So let's have some idea about brute force attack, which is easiest, but in most cases hardest way.
In cryptography, a brute force attack consists of an attacker submitting many passwords or passphrases with the hope of eventually guessing correctly. The attacker systematically checks all possible passwords and passphrases until the correct one is found. Alternatively, the attacker can attempt to guess the key, which is typically created from the password using a key derivation function. This is known as an exhaustive key search. A brute force attack is a cryptanalytic attack that can, in theory, be used to attempt to decrypt any encrypted data, except for data encrypted in an information theoretically secure manner. Such an attack might be used when it is not possible to take advantage of other weaknesses in an encryption system, if any exist, that would make the task easier. When password guessing, this method is very fast when used to check all short passwords, but for longer passwords other methods such as the dictionary attack are used because a brute force search takes too long. Longer passwords, passphrases and keys have more possible values, making them exponentially more difficult to crack than shorter ones. Brute force attacks can be made less effective by obfuscating the data to be encoded, making it more difficult for an attacker to recognize when the code has been cracked, or by making the attacker do more work to test each guess. One of the measures of the strength of an encryption system is how long it would theoretically take an attacker to mount a successful brute force attack against it.
Okay, so there is a basic concept. So the basic concept is
Brute force attacks work by calculating every possible combination that could make up a password and testing it to see if it is the correct password. As the password's length increases, the amount of time, on average, to find the correct password increases exponentially. The resources required for a brute force attack grow exponentially with increasing key size, not linearly. Although U.S. export regulations historically restricted key lengths to 56-bit symmetric keys, e.g. data encryption standard, these restrictions are no longer in place, so modern symmetric algorithms typically use computationally stronger 128 to 256-bit keys. There is a physical argument that a 128-bit symmetric key is computationally secure against brute force attack. The so-called Landauer limit implied by the laws of physics sets a lower limit on the energy required to perform a computation of kT lane 2 per bit erased in a computation, where T is the temperature of the computing device in kelvins, K is the Boltzmann constant, and the natural logarithm of 2 is about 0.693. No irreversible computing device can use less energy than this, even in principle. Thus, in order to simply flip through the possible values for a 128-bit symmetric key, ignoring doing the actual computing to check it would, theoretically, require 2128 minus 1-bit flips on a conventional processor. If it is assumed that the calculation occurs near room temperature, approximately 300 K, the von Neumann-Landauer limit can be applied to estimate the energy required as approximately 1018 joules, which is equivalent to consuming 30 gigawatts of power for 1 year. This is equal to 30 times 109 W times 365 times 24 times 3600 S equals 9.46 times 1017 J or 262.7 terawatt hours, about 0.1% of the yearly world energy production. The full actual computation, checking each key to see if a solution has been found, would consume many times this amount. Furthermore, this is simply the energy requirement for cycling through the key space. The actual time it takes to flip each bit is not considered, which is certainly greater than 0.
so they made an assumption about testing all the possible key combinations with 128 with symmetric key, and it takes about 0.1% of the yearly world energy production, which is huge. And the actual required energy would be much higher than that. So just from energy wise, it is not doable.
AES permits the use of 256-bit keys. Breaking a symmetric 256-bit key by brute force requires 2,128 times more computational power than a 128-bit key. One of the fastest supercomputers in 2019 has a speed of 100 pevflops 6, which could theoretically check 100 million 1014 AES keys per second, assuming 1000 operations per check, but would still require 3.67 times 1055 years to exhaust the 256-bit key space.
So you see, even the supercomputer takes forever. Yeah, it is like forever to exhaust 256-bit key space. Okay, so what is AES? If you wonder, let's read it.
Advanced Encryption Standard.
And what is symmetric and asymmetric key difference? I'm trying to find an easy explanation. Okay, let's read them.
Symmetric encryption. This is said to be the simplest and best known encryption technique. As discussed already, it uses one key for both encryption and decryption. Because the algorithm behind symmetric encryption is less complex and executes faster, this is the preferred technique when transmitting data in bulk. The plaintext is encrypted using a key, and the same key is used at the receiving end to decrypt the received ciphertext. The host in the communication process would have received the key through external means. Widely used symmetric encryption algorithms include AES 128, AES 192, and AES 256.
So the key point here, external means. So you don't provide, of course, you don't provide the ciphering key with the communication. Let's say you have two computers and you have physical access to them. You install both of them a key, and you can symmetrically encrypt and decrypt your data between those two computers because you have installed the key to those computers yourselves physically. Okay. And asymmetric encryption.
Asymmetric encryption. This type of encryption is relatively new as compared to symmetric encryption, and is also referred to as public key cryptography. Asymmetric encryption is considered to be more secure than symmetric encryption as it uses two keys for the process. The public key used for encryption is available to everyone, but the private key is not disclosed. This encryption method is used in everyday communication over the internet. When a message is encrypted using a public key, it can only be decrypted using a private key. However, when a message is encrypted using a private key, it can be decrypted using a public key. Digital certificates in the client-server model can be used to discover public keys. The drawback of this encryption is that it takes more time than the symmetric encryption process. Common asymmetric encryption techniques include RSA, DSA, and PKCS. Key differences. Now that we have a basic understanding of both the encryption types, let's glance through the key differences between them. Symmetric encryption is an old technique, while asymmetric encryption is the newer one. Asymmetric encryption takes longer to execute because of the complex logic involved. For this reason, symmetric encryption is used when transmitting data in bulk. Asymmetric data is more secure because it uses different keys for the encryption and decryption process. While both of these have their own pros and cons, asymmetric encryption is definitely a better choice from the security perspective.
Okay, let's continue. We will have more information. Okay, I think we have seen enough information about brute force attack. So there are attack models, and let's see them.
Attack models: 19 known ciphertext, known plaintext, chosen plaintext, adaptive, chosen ciphertext, adaptive. What are the goals of the attacker? Find the secret plaintext or part of the plaintext. Find the encryption key. Distinguish the encryption of two different plaintexts. How clever is the attacker? Does secure ciphers exist? What is a secure cipher? Perfect security. Computational security. Provable security. ETCRRM, Electronic Teleprinter Cryptographic Regenerative Repeater Mixer, ETCRRM. Invented by the Norwegian Army Signal Corps in 1950, Bjorn Rorhold, Kerr Masingseth, produced by STK. Used for hot line between Moskva and Washington, about 2,000 devices produced.
So they produced a device to have secure communication between Moscow and Washington. Okay. White House crypto room in 1960s, because in those years there weren't secure communication with like we have currently. There is also producing key tape for one-time pads. When you search for it, you can find more information about it.
In cryptography, the one-time pad (OTP) is an encryption technique that cannot be cracked, but requires the use of a one-time pre-shared key the same size as, or longer than, the message being sent. In this technique, a plaintext is paired with a random secret key, also referred to as a one-time pad. Then, each bit or character of the plaintext is encrypted by combining it with the corresponding bit or character from the pad using modular addition. The resulting ciphertext will be impossible to decrypt or break if the following four conditions are met. 1, 2. The key must be truly random. The key must be at least as long as the plaintext. The key must never be reused in whole or in part. The key must be kept completely secret. It has also been proven that any cipher with the property of perfect secrecy must use keys with effectively the same requirements as OTP keys. 3. Digital versions of one-time pad ciphers have been used by nations for critical diplomatic and military communication, but the problems of secure key distribution have made them impractical for most applications.
So the key point of this is the key sharing. So it says pre-shared key. To have a pre-shared key,
in cryptography, a pre-shared key (PSK) is a shared secret which was previously shared between the two parties using some secure channel before it needs to be used.
so in this case, it would be like physically delivering the key between nations to use one-time keys. It is extremely secure. However, the key sharing is the hardest part of this. You can get more information about this if you want. You see there are many information. Okay, let's continue. Symmetric encryption.
Symmetric encryption 24. Is it possible to design secure and practical crypto?
Okay, I will take a pause. Okay, so
Stream cipher versus block cipher.
let's look better explanation for this.
Both block cipher and stream cipher belongs to the symmetric key cipher. These two, block cipher and stream cipher, are the methods used for converting the plain text into ciphertext. The main difference between block cipher and stream cipher is that block cipher converts the plain text into ciphertext by taking plain text's block at a time, while stream cipher converts the plain text into ciphertext by taking one byte of plain text at a time.
Okay, let's see the difference between them.
Let's see the difference between them. 1. Block cipher converts the plain text into ciphertext by taking plain text's block at a time. Stream cipher converts the plain text into ciphertext by taking one byte of plain text at a time. 2. Block cipher uses either 64 bits or more than 64 bits, while stream cipher uses 8 bits. 3. The complexity of block cipher is simple, while stream cipher is more complex. 4. Block cipher uses confusion as well as diffusion, while stream cipher uses only confusion. 5. In block cipher, reverse encrypted text is hard, while in stream cipher, reverse encrypted text is easy. 6. The algorithm modes which are used in block cipher are ECB, electronic code book, and CBC, cipher blockchaining. The algorithm modes which are used in stream cipher are CFB, cipher feedback, and OFB, output feedback. 7. Block cipher works on transposition techniques like Caesar cipher, polygram substitution cipher, etc., while stream cipher works on substitution techniques like rail fence technique, columnar transposition technique, etc. 8. Block cipher is slow as compared to stream cipher, while stream cipher is fast in comparison to block cipher.
Okay, we can get
Both block and stream cipher are the methods of encryptions which are primarily used for converting the plain text into ciphertext directly and belong to the family of symmetric key ciphers. Following are the important differences between block cipher and stream cipher.
Okay, I think pretty much same information. And let's continue. There is symmetric stream cipher, and this is the way it works. And the linear feedback shift register. Let's have some idea about this.
In computing, a linear feedback shift register (LFSR) is a shift register whose input bit is a linear function of its previous state. The most commonly used linear function of single bits is exclusive or XOR. Thus, an LFSR is most often a shift register whose input bit is driven by the XOR of some bits of the overall shift register value. The initial value of the LFSR is called the seed, and because the operation of the register is deterministic, the stream of values produced by the register is completely determined by its current or previous state. Likewise, because the register has a finite number of possible states, it must eventually enter a repeating cycle. However, an LFSR with a well-chosen feedback function can produce a sequence of bits that appears random and has a very long cycle. Applications of LFSRs include generating pseudo-random numbers, pseudo-noise sequences, fast digital counters, and whitening sequences. Both hardware and software implementations of LFSRs are common. The mathematics of a cyclic redundancy check, used to provide a quick check against transmission errors, are closely related to those of an LFSR. 1.
Using Cryptography.
Uses in cryptography, edit, LFSRs have long been used as pseudo-random number generators for use in stream ciphers, especially in military cryptography, due to the ease of construction from simple electromechanical or electronic circuits, long periods, and very uniformly distributed output streams. However, an LFSR is a linear system, leading to fairly easy cryptanalysis. For example, given a stretch of known plaintext and corresponding ciphertext, an attacker can intercept and recover a stretch of LFSR output stream used in the system described, and from that stretch of the output stream can construct an LFSR of minimal size that simulates the intended receiver by using the Berlekamp-Massey algorithm. This LFSR can then be fed the intercepted stretch of output stream to recover the remaining plaintext. 3 general methods are employed to reduce this problem in LFSR-based stream ciphers: nonlinear combination of several bits from the LFSR state, nonlinear combination of the output bits of 2 or more LFSRs, see also, shrinking generator, or using evolutionary algorithm to introduce nonlinearity. 8. Irregular clocking of the LFSR, as in the alternating step generator. Important LFSR-based stream ciphers include A5.1 and A5.2, used in GSM cell phones, E0, used in Bluetooth, and the shrinking generator. The A5.2 cipher has been broken and both A5.1 and E0 have serious weaknesses. 9.10. The linear feedback shift register has a strong relationship to linear congruential generators. 11.
Okay, so the LFSR is also not a strong one. And there is symmetric block cipher.
The algorithm represents a family of permutations of the message space, normally designed by iterating a less secure round function, may be applied in different operational modes, must be impossible to derive K based on knowledge of P and C.
And there is iterated block cipher design. Let's look for this one. Okay.
Most block cipher algorithms are classified as iterated block ciphers, which means that they transform fixed-size blocks of plaintext into identically sized blocks of ciphertext, via the repeated application of an invertible transformation known as the round function, with each iteration referred to as a round. 12. Usually, the round function R takes different round keys key as second input, which are derived from the original key. Given one of the standard iterated block cipher design schemes, it is fairly easy to construct a block cipher that is cryptographically secure, simply by using a large number of rounds. However, this will make the cipher inefficient. Thus, efficiency is the most important additional design criterion for professional ciphers. Further, a good block cipher is designed to avoid side-channel attacks, such as branch prediction and input-dependent memory accesses that might leak secret data via the cache state or the execution time. In addition, the cipher should be concise, for small hardware and software implementations. Finally, the cipher should be easily cryptanalyzable, such that it can be shown how many rounds the cipher needs to be reduced to, so that the existing cryptographic attacks would work, and, conversely, that it can be shown that the number of actual rounds is large enough to protect against them.
Okay, there is substation permutation network. It is here.
One important type of iterated block cipher known as a substitution permutation network (SPN) takes a block of the plaintext and the key as inputs, and applies several alternating rounds consisting of a substitution stage followed by a permutation stage, to produce each block of ciphertext output. 13. The nonlinear substitution stage mixes the key bits with those of the plaintext, creating Shannon's confusion. The linear permutation stage then dissipates redundancies, creating diffusion. 14. 15. A substitution box (S-box) substitutes a small block of input bits with another block of output bits. This substitution must be one-to-one, to ensure invertibility, hence decryption. A secure S-box will have the property that changing one input bit will change about half of the output bits on average, exhibiting what is known as the avalanche effect, i.e., it has the property that each output bit will depend on every input bit. 16. A permutation box (P-box) is a permutation of all the bits. It takes the outputs of all the S-boxes of one round, permutes the bits, and feeds them into the S-boxes of the next round. A good P-box has the property that the output bits of any S-box are distributed to as many S-box inputs as possible. Citation needed at each round. The round key, obtained from the key with some simple operations, for instance, using S-boxes and P-boxes, is combined using some group operation, typically XOR. Citation needed. Decryption is done by simply reversing the process using the inverses of the S-boxes and P-boxes and applying the round keys in reversed order. 17. A sketch of a substitution permutation network with 3 rounds, encrypting a plaintext block of 16 bits into a ciphertext block of 16 bits. The S boxes are the C, the P boxes are the same P, and the round keys are the key.
Okay, you see, these are all very advanced algorithms, and understanding them would require a huge amount of time and test and trial and examples. So just have an idea about them at the moment. Okay, 1 minute. Okay, let's continue.
Data Encryption Standard 31, published in 1977 by the U.S. National Bureau of Standards for use in unclassified government applications with a 15-year lifetime, 16-round Feistel cipher with 64-bit data blocks, 56-bit keys. 56-bit keys were controversial in 1977. Today, exhaustive search on 56-bit keys is very feasible. Controversial because of classified design criteria, however no loophole was ever found.
So this architecture, to get more idea, search this architecture, and I think I need to type the full name. Okay, there are many architectures. This one looks better. And there is also a DES cracker. I think we can read more about it on the Wikipedia.
In cryptography, the F-Day cracker, nicknamed Deep Crack, is a machine built by the Electronic Frontier Foundation (F) in 1998 to perform a brute force search of the data encryption standard (DE) cipher's key space, that is, to decrypt an encrypted message by trying every possible key. The aim in doing this was to prove that the key size of DE was not sufficient to be secure. The EFF's $250,000 DE cracking machine contained 1,856 custom chips and could brute force a DE key in a matter of days. The photo shows a two-sided DE cracker circuit board fitted with 64 deep crack chips.
Okay, let's see some background.
DE uses a 56-bit key, meaning that there are 256 possible keys under which a message can be encrypted. This is exactly 72,57,594,037,927,936, or approximately 72 quadrillion possible keys. One of the major criticisms of DE, when proposed in 1975, was that the key size was too short. Martin Hellman and Whitfield Diffie of Stanford University estimated that a machine fast enough to test that many keys in a day would have cost about $20 million in 1976, an affordable sum to national intelligence agencies such as the U.S. National Security Agency. Subsequent advances in the price-performance of chips kept reducing that cost until 20 years later it became affordable for even a small nonprofit organization such as the F to mount a realistic attack.
Okay. Okay, let's read this one as well.
The DE Challenges Edit DE was a federal standard, and the U.S. government encouraged the use of DE for all non-classified data. RSA Security wished to demonstrate that DES's key length was not enough to ensure security, so they set up the DE Challenges in 1997, offering a monetary prize. The first DE challenge was solved in 96 days by the DESCHALL project led by Rock Verser in Loveland, Colorado. RSA Security set up Day Challenge E1, which was solved by Distributed.net in 39 days in January and February 1998. 3. In 1998, the F built Deep Crack, named in reference to IBM's Deep Blue chess computer, for less than $250,000. 4. In response to Day Challenge E2, on July 15, 1998, Deep Crack decrypted a day encrypted message after only 56 hours of work, winning $10,000. The brute force attack showed that cracking Day was actually a very practical proposition. Most governments and large corporations could reasonably build a machine like Deep Crack. 6 months later, in response to RSA Security's Day Challenge 3, and in collaboration with Distributed.net, the F used Deep Crack to decrypt another day encrypted message, winning another $10,000. This time, the operation took less than a day, 22 hours and 15 minutes. The decryption was completed on January 19, 1999. In October of that year, Day was reaffirmed as a federal standard, but this time the standard recommended triple Day. The small key space of Day, and relatively high computational costs of triple Day resulted in its replacement by AES as a federal standard, effective May 26, 2002. In many ways, such projects signaled that the hard cypherpunks-minded way of thinking about applied cryptography had reached its peak.
And you can read more about this. Outdated by now. Single disk cannot be considered as a secure block cipher. Use 3 disks. Advanced encryption standards.
Advanced Encryption Standard. Public competition to replace Day, because 56-bit keys and 64-bit data blocks no longer adequate. Reindahl nominated as the new Advanced Encryption Standard (AES) in 2001, FIPS 197. Reindahl, pronounced as Reindahl, designed by Vincent Ryman and Joan Dayman, 128-bit block size, note error in Harris P. 809. 128-bit, 196-bit, and 256-bit key sizes. Reindahl is not a Feistel cipher.
So, Advanced Encryption Standard, which is IAS.
Advanced Encryption Standard.
I think it is still being used. Let's read it. I will use 1 second.
The Advanced Encryption Standard, AES, also known by its original name Rigidal, Dutch pronunciation, Rindel, 3, is a specification for the encryption of electronic data established by the U.S. National Institute of Standards and Technology, NIST, in 2001-4. AES is a subset of the Rigidal block cipher, 3, developed by 2 Belgian cryptographers, Vincent Rijman and Joan Dayman, who submitted a proposal, 5, to NIST during the AES selection process. 6. Rigidal is a family of ciphers with different key and block sizes. For AES, NIST selected 3 members of the Rigidal family, each with a block size of 128 bits, but 3 different key lengths: 128, 192, and 256 bits. AES has been adopted by the U.S. government and is now used worldwide. It supersedes the Data Encryption Standard (DES), 7, which was published in 1977. The algorithm described by AES is a symmetric key algorithm, meaning the same key is used for both encrypting and decrypting the data. In the United States, AES was announced by the NIST as US FIPS Pub 197, FIPS 197, on November 26, 2001. This announcement followed a 5-year standardization process in which 15 competing designs were presented and evaluated before the Rigidal cipher was selected as the most suitable. See Advanced Encryption Standard process for more details. AES is included in the ISO/IEC 18033-3 standard. AES became effective as a U.S. federal government standard on May 26, 2002, after approval by the U.S. Secretary of Commerce. AES is available in many different encryption packages, and is the first, and only, publicly accessible cipher approved by the U.S. National Security Agency, NSA, for top-secret information when used in an NSA-approved cryptographic module. See Security of AES, below.
Okay, so let's return.
Best public cryptanalysis attacks have been published that are computationally faster than a full brute force attack, though none as of 2013 are computationally feasible. 1. For AES 128, the key can be recovered with a computational complexity of 2126.1 using the biclique attack. For biclique attacks on AES 192 and AES 256, the computational complexities of 2189.7 and 2254.4 respectively apply. Related key attacks can break AES 192 and AES 256 with complexities 299.5 and 2176 in both time and data, respectively. 2.
Okay, so we can say that it is not possible to crack these within within a reasonable data with reasonable time period. Okay, so currently our HTTPS is using RSA 2048 bits. Okay, let's continue. So this is the advanced encryption standard, and there is regional round function, which is the selected method for a advanced encryption standard. You can get more idea about it on other sources. Okay, so it uses key mix, rounds containing byte substitution, row shift, column mix, key mix, plus round containing byte substitution, row shift, and key mix. These are very advanced algorithms, and they are extremely hard to understand. If you are not going to try improve such algorithm, you shouldn't spend time to code them yourself. Just use them as there are frameworks.
Block ciphers can be used in different modes in order to provide different security services. Common modes include:
Okay, let's search for them.
Electronic Code Book (ECB) is a mode of operation for a block cipher with the characteristic that each possible block of plaintext has a defined corresponding ciphertext value and vice versa. In other words, the same plaintext value will always result in the same ciphertext value.
One second. Okay, so
Most modes require a unique binary sequence, often called an initialization vector (IV), for each encryption operation. The IV has to be non-repeating and, for some modes, random as well. The initialization vector is used to ensure distinct ciphertexts are produced even when the same plaintext is encrypted multiple times independently with the same key. Citation needed. Block ciphers may be capable of operating on more than one block size, but during transformation the block size is always fixed. Block cipher modes operate on whole blocks and require that the last part of the data be padded to a full block if it is smaller than the current block size. 2. There are, however, modes that do not require padding because they effectively use a block cipher as a stream cipher.
Okay, and output feedback, hyper feedback, counter mode, and Gauss counter mode, and such. Okay, plain text, ciphertext using ACB mode, which is this one, and ciphertext using secure mode. As you can see, nothing can be visible. This is just for illustration purposes. Integrity check functions, hash functions. Okay, hash functions are very commonly used in security. It is used for both verification of data and okay, and many other things. Let's see the applications.
Applications of hash functions. Protection of password. Comparing files. Authentication of SW distributions. Bitcoin. Generation of message authentication codes, MAC. Digital signatures. Pseudo number generation, mask generation functions. Key derivation.
Okay.
Hash functions, message digest functions. Requirements for a one-way hash function h. 1. Ease of computation. Given x, it is easy to compute h x. 2. Compression. H maps inputs x of arbitrary bit length to outputs h x of a fixed bit length n. 3. One way. Given a value y, it is computationally infeasible to find an input x so that h x equals y. 4. Collision resistance. It is computationally infeasible to find x and x, where x does not equal x, with h x equals h x. Note, two variants of this property.
Okay, there are properties and frequently used hash functions. Some of them are very popular. Maybe you already heard of them.
MD5 to 128-bit digest. Broken. Often used in Internet protocols but no longer recommended. SHA-1, secure hash algorithm, 160-bit digest. Potential attacks exist. Designed to operate with the U.S. Digital Signature Standard (DSA), SHA-256, 384, 512-bit digest. Still secure. Replacement for SHA-1. RIPEMD-160 to 160-bit digest. Still secure. Hash function frequently used by European cryptographic service providers. NIST competition for new secure hash algorithm, closed in 2012 with the winner.
Okay, I think this information is incorrect. MD5 is 32-bit if I remember correctly. Let's see it. Oh, 100. Correct. Let's read it.
The MD5 message digest algorithm is a widely used hash function producing a 128-bit hash value.
Oh, bit hash function.
Although MD5 was initially designed to be used as a cryptographic hash function, it has been found to suffer from extensive vulnerabilities. It can still be used as a checksum to verify data integrity, but only against unintentional corruption. It remains suitable for other non-cryptographic purposes, for example for determining the partition for a particular key in a partition database.
Okay, and MD5 is one of the most popular hashing function. It was used for a long time. Let's use online MD5. This is one way, but there can be lots of, let's say, collisions. Okay, for example, I am going to just MD5 the key ladder. You see it generates text length of this. Let's see the length of the text. Okay, it is 32 character, and each character is hexadecimal, as you can see, and one hexadecimal is how many bits? How many bits you can represent numbers from 1, 2, 3, 4, 5, 6 until A, B, C, D, E. Okay, so between 0 and 15, how many bits you need? You need only 4 bits. Okay, why? 1, 1, 1, 1, 1 equal to 16. Okay, so each character is 4 bit and have 32 character. It means it is 128 bits. So this is correct. And this equivalent of MD5, equivalent of, let's say, the T character in SHI1, you see it is now how many letters? Now 40 letters. So still hexadecimal. So this is 40 multiplied with 4, 160. Yes. And SH 256 is 64 characters, so it is 256 bits. Okay, so this is the uh, hashing functions. SH 256 is a very secure algorithm still. It is extremely hard to crack. Perhaps we can see some statistics about it. Brute force, let's see. Maybe there is some information. Okay, so they provide some searching. I will just search. Let's say this one. Oh, okay. So you see, uh, an NVIDIA 560 GTX GPU can check 1,800,000,000 MD5 hashes per second, and the other algorithms are shown like this, but it still doesn't show us okay. So there is a rough estimation.
In your case, breaking the hash algorithm is equivalent to finding a collision in the hash algorithm. That means you don't need to find the password itself, which would be a pre-image attack. You just need to find an output of the hash function that is equal to the hash of a valid password, thus collision. Finding a collision using a birthday attack takes O2 time, where n is the output length of the hash function in bits. SHA-2 has an output size of 512 bits, so finding a collision would take O2 to the power of 256 time. Given there are no clever attacks on the algorithm itself, currently none are known for the SHA-2 hash family, this is what it takes to break the algorithm. To get a feeling for what 2 to the power of 256 actually means, currently it is believed that the number of atoms in the entire universe is roughly 10 to the power of 80, which is roughly 2 to the power of 266. Assuming 32-byte input, which is reasonable for your case 20 bytes salt plus 12 bytes password, my machine takes approximately 0.22s, approximately 2 to the power of minus 2s, for 65,536 equals 2 to the power of 16 computations. So 2 to the power of 256 computations would be done in 2 to the power of 240 asterisk 2 to the power of 16 computations, which will take
10 power 64 years. You see, it's almost like eternity.
Even calling this millions of years is ridiculous. And it doesn't get much better with the fastest hardware on the planet computing thousands of hashes in parallel. No human technology will be able to crunch this number into something acceptable. So forget brute forcing SHA-256 here. Your next question was about dictionary words. To retrieve such weak passwords, rainbow tables were used traditionally. A rainbow table is generally just a table of precomputed hash values. The idea is if you were able to precompute and store every possible hash along with its input, then it would take you 1 to look up a given hash and retrieve a valid preimage for it. Of course, this is not possible in practice since there's no storage device that could store such enormous amounts of data. This dilemma is known as memory time trade-off. As you are only able to store so many values, typical rainbow tables include some form of hash chaining with intermediary reduction functions. This is explained in detail in the Wikipedia article, to save on space by giving up a bit of savings in time. Salts were a countermeasure to make such rainbow tables infeasible. To discourage attackers from precomputing a table for a specific salt, it is recommended to apply per-user salt values. However, since users do not use secure, completely random passwords, it is still surprising how successful you can get if the salt is known and you just iterate over a large dictionary of common passwords in a simple trial and error scheme. The relationship between natural language and randomness is expressed as entropy. Typical password choices are generally of low entropy, whereas completely random values would contain a maximum of entropy. The low entropy of typical passwords makes it possible that there is a relatively high chance of one of your users using a password from a relatively small database of common passwords. If you Google for them, you will end up finding torrent links for such password databases, often in the gigabyte size category. Being successful with such a tool is usually in the range of minutes to days if the attacker is not restricted in any way. That's why generally hashing and salting alone is not enough, you need to install other safety mechanisms as well. You should use an artificially slowed down entropy-inducing method such as PBKDF2 described in PKCS number 5, and you should enforce a waiting period for a given user before they may retry entering their password. A good scheme is to start with 0.5s and then doubling that time for each failed attempt. In most cases users don't notice this and don't fail much more often than 3 times on average. But it will significantly slow down any malicious outsider trying to attack your application.
So what does this mean? This means that, let's say you are building a website, you should not let clients to try their password again and again and again and again. Okay. But usually websites, blogs, and IP after trying, let's say, 5 times, and then the IP is blocked like 15 minutes, and if the repeated password try failure happens, the IP of the client is blocked even more. This prevents attackers to try many different passwords, and if the user's password is weak, finding the correct password is prevented. So it also says salting passwords. Salting is basically adding random data to the each user's password.
In cryptography, a salt is random data that is used as an additional input to a one-way function that hashes data, a password or passphrase. Salts are used to safeguard passwords in storage. Historically, a password was stored in plaintext on a system, but over time additional safeguards were developed to protect the user's password against being read from the system. A salt is one of those methods. A new salt is randomly generated for each password. In a typical setting, the salt and the password or its version after key stretching are concatenated and processed with a cryptographic hash function, and the output hash value, but not the original password, is stored with the salt in a database. Hashing allows for later authentication without keeping and therefore risking exposure of the plaintext password in the event that the authentication data store is compromised. Salts defend against a pre-computed hash attack, e.g. rainbow tables. 1. Since salts do not have to be memorized by humans, they can make the size of the hash table required for a successful attack prohibitively large without placing a burden on the users. Since salts are different in each case, they also protect commonly used passwords, or those users who use the same password on several sites, by making all salted hash instances for the same password different from each other.
So this is salting, and let's say both users are using the same password. However, you use different salt value, so string to be hashed becomes like this and like this. And the hashed value becomes like this. However, let's say your database is hacked, and if the hacker can also read the salt value, they can still try the weak passwords, or they can still try to common passwords database and decrypt the password. However, salting will prevent hacker to use rainbow tables. With rainbow tables, they can instantly find the password. So what is rainbow table?
A rainbow table is a precomputed table for caching the output of cryptographic hash functions, usually for cracking password hashes. Tables are usually used in recovering a key derivation function or credit card numbers, etc., up to a certain length consisting of a limited set of characters. It is a practical example of a space-time trade-off, using less computer processing time and more storage than a brute force attack which calculates a hash on every attempt, but more processing time and less storage than a simple key derivation function with one entry per hash. Use of a key derivation that employs a salt makes this attack infeasible.
So let's say you have a rainbow table of SHA-256 that contains 1 billion common used passwords. And if you add a salt value to your hashes, and if let's say you are using SHA-256 hashing, that then 2 billion passwords having a rainbow table becomes obsolete. It can't be used because it just stores the hashed values of the default passwords. When you even add a single character to the user password, that pre-calculated rainbow table becomes unusable. Okay, so this is the reason why we add a salt value. And if each time you are generating a random salt value, that means they can't possibly have a rainbow table for quickly checking the user uh, password against pre-computed table. Okay. In MD5, it is feasible for supercomputers to test all the possible passwords and find a collision. Cases, maybe there are some uh, so you see a modern GPU can guess 3.2 million guesses a second. Okay. Okay, so let's read how crackable is a given password. This is a good example.
How crackable is a given password? You need to assume a service you're using is run by reasonably competent system administrators and that they are, at a minimum, storing hashed passwords rather than plain text. For safety's sake, assume they're using a weak hashing algorithm. In this case, we'll assume one round of salted MD5. Note that we're giving them the benefit of the doubt that they're actually salting their passwords. If your password is 9 characters of lowercase numbers and letters, that gives you 101,559,956,668,416 possible passwords. 36 to the power of 9.
Okay. Why 36 to the power of 9? Because if you are using lowercase numbers and letters, there are 36 different letters, including numbers. And if it is 9 characters, then you have 36 to the power of 9. It will be 36 character for first letter, 36 character for second letter, 36 character for third letter, 36 character for the fourth letter, and so on. So this is the number of uh, characters you can use. So you can generate that number of different um, passwords with these, let's say, character space.
At WordFence, we have an 8 GPU cluster that can crack salted MD5 at a rate of 90.6 billion salted MD5 guesses per second. It will take us 1,128 seconds or 18 minutes to crack your password if we are guessing every single combination of letter and number 9 characters long. We can do it faster than that if we exclude certain patterns. Now you begin to understand why longer passwords are better. You also begin to see why you should not just use letters and numbers, but special characters too. Any password that uses just letters and numbers is weak. Here's why.
So you see, they can under 20 minutes crack your any 9 character length password if they are only small letters and numbers. Uppercase also make difference. These are case sensitive. Hashing is case sensitive. Okay, so here's some calculations.
If you have a password made of just ones and zeros and it's 4 digits long, you will have 12 to the power of 4 possible passwords or 16 possible passwords. If you have a password made of the digits 0 to 9, that is 10 possible characters, and it is 4 digits long, you have 10 to the power of 4, which is 10,000 possible combinations.
So in brute force, if there is no tuning, every combination is tested, and if there is an hardware that is fast enough to test every combination possible in that character space, it can be easily cracked. Okay.
Now if you instead build your password out of all lowercase letters, uppercase letters, numbers and a set of 10 symbols, you have 26 plus 26 plus 10 plus 10 equals 72 possible characters. So if you have a password that is just 4 characters long, you now have 72 to the power of 4 possible passwords, which is 26,873,856 possible passwords.
So you see, with increasing your character space, the number of combinations increases exponentially.
As you can see, every time you increase the number of characters your password is made up of, you get a huge increase in the number of possible passwords, even though you keep the length at just 4 characters in our example. You get 26 million possible passwords from just 4 characters if you use a wider range of characters in your password. That really illustrates how important it is to use uppercase, lowercase, numbers and symbols in your password. If you now expand the length of your password to 12 characters, you have 72 to the power of 12 or 19 sextillion 408 quintillion 409 quadrillion 961 trillion 765 billion 342,806,016. Even with our 8 GPU cluster, it would take us 2,495,937 days or 6,838 years to guess your password if we try every possible combination.
So you see, it becomes infeasible to do in a relative time.
We would consider a 12-character password that uses random, see next paragraph, uppercase letters, lowercase letters, numbers and symbols to be a strong password. And to be clear, it is a strong password even if the service you're using is storing passwords using one salted round of MD5, which is relatively weak. For comparison, WordPress uses over 8,000 rounds of salted MD5, which of course makes it 8,000 times slower for a hacker to crack WordPress passwords. It is important to note that your password should be random characters and not made up of patterns like beginning or ending with a number or dictionary words. As soon as you introduce dictionary words and predictable patterns into passwords, they become significantly easier to guess because a password cracker can simply exclude everything that does not match a predictable pattern. As computers get faster at hashing, what will developers do? If the trend over the last few years is anything to go by, reverse engineering hashed passwords back into their plain text is going to keep getting faster at an increasing rate. The GPU cluster that we built to audit passwords for WordFence customers is faster at hashing than the fastest computer on Earth in 2003. This is an illustration of how fast computing power is increasing. The past 5 years has seen an explosion in purpose-built hardware that does what a CPU would previously have been used for. The difference is that this hardware processes in parallel and is therefore much faster. The consumer gaming GPUs that we have discussed above contain over 2,000 cores that can do calculations in parallel. Another area that has been fuel for innovation in parallel computing is Bitcoin mining hardware. You can buy ASICs and FPGAs, which are both ways of creating an application on a chip, and both can perform tasks like hashing in a massively parallel fashion. Bitcoin miners use ASICs and FPGAs for mining and have driven the price of this hardware down. It can also be used to crack passwords in parallel and at very high speed. ASIC application-specific integrated circuit. A field programmable gate array (FPGA) is an integrated circuit designed to be configured by a customer or a designer after manufacturing.
Okay, so can we use better hashing algorithms?
Can we use better hashing algorithms? In computer science, we usually strive to make algorithms faster. Paradoxically, a better hashing algorithm for passwords is one that is slower or computationally more expensive. The benefit of a more expensive and slower hashing algorithm is that if you can slow down how long it takes to hash a password, you are slowing down how fast hackers can guess passwords. Algorithms like BCRYPT let you specify complexity, which affects the speed at which hashing occurs and therefore the speed at which guessing occurs. Another useful algorithm is script, which is designed to make it difficult to do calculations in parallel. That means that a hacker can no longer use the 2000 cores in their GPU to try to crack your password at the same time. They instead need to make one guess at a time. These options are not without problems. Application developers like Facebook and Google want to provide useful services to you. They become popular and have tens of thousands of customers that want to log in. If they use a hashing algorithm that takes, say, 5 seconds per hashed password on a server, that means they need 5 servers just to allow 1 user per second. They would need 50,000 servers to be able to allow 10,000 users per second to sign in. For Facebook, that might be unacceptable and they may opt for a faster but weaker hashing algorithm. There are a few interesting options to allow slower hashing without overloading servers that are being discussed in the information security community. One of them is quite simple and it's called server relief. The way server relief works is it uses a slower hashing algorithm like BCRYPT or script, and actually does most of the hashing in your web browser when you are signing in. That uses your workstation's CPU instead of the computing power of the servers belonging to the service that you are signing into. A hash that took longer to calculate is then sent by your web browser to the server you are signing into, which turns that into a salted SHA-256 hash and stores it. The effect is that you used a CPU-intensive hashing algorithm that might be hard to parallelize and is slower. Your web browser did most of the computation, which saved valuable CPU cycles on the server you are signing into. This would allow an authentication server to handle a large number of customers signing in and to use a computationally expensive hashing algorithm without getting overloaded. Conclusion that concludes our introduction to hashing and passwords. We have covered the history of password storage, why password hashing is used, what rainbow tables are and how salted passwords defeat a rainbow tables attack. We have also discussed how password cracking is done and how hardware like GPUs, ASICs and FPGAs can accelerate cracking. We also gave you a brief introduction to algorithms that make it more difficult to crack passwords and a performance architecture that allows the use of a strong hashing algorithm without overloading servers.
So the title of the page is Password Authentication and Password Cracking. If you search Google for it, you can see on wordfans.com. Okay, this is a very good page to read. I think I will add this to the slides. frequently used hash functions. Okay, and I need to change the, let's see, can I give it a, I think this looks cool. Okay, I will update the PDF file later. Okay, so why do we, if we are going to test every possible password combination, why does it make difference between MD5 or SH 256 or SH1? The difference is the calculation time of hashing and the collision. The collision is also very important. So let's search for let's see if there is a good. Okay, these two images have the same MD5 hash. You see they are completely different images, but they have the same hashing value. So this is why MD5 collision. This is why MD5 is weak. Okay, so I'm trying to go find a good explanation. Collision. Okay, collision vulnerabilities and collision attack. Okay, let's read more about this.
In cryptography, a collision attack on a cryptographic hash tries to find two inputs producing the same hash value, i.e. a hash collision. This is in contrast to a preimage attack where a specific target hash value is specified. There are roughly two types of collision attacks. Collision attack find two different messages M1 and M2 such that hash M1 equals hash M2. More generally, chosen prefix collision attack given two different prefixes P1 and P2, find two appendages M1 and M2 such that hash P1M1 equals hash P2M2, where denotes the concatenation operation.
So the collision attack is much easier to achieve in lower bits having hashing functions. Okay, that is why MD5 is pretty weak in terms of collision, because you can generate a collision and assume that your let's say system to uh, uh, behave show the same behavior for the same for the different type of different data. So this is a good example of collision attack. Let's say you store an image MD5 data on your database to verify the incoming data security or integrity. The hackers, let's say you are storing MD5 of an exe to verify integrity of your exe file. the hackers implement or insert, let's say, password stealers to that exe, and then modify its MD5 to be to make it same as your stored MD5. So your system wouldn't understand the difference, or your clients wouldn't understand the difference, because they would have same MD5 hash value. So your system or the clients would think that this is the unmodified exe file. However, it would be the modified exe file. That is why MD5 is weak. And also calculating MD5 is faster. Therefore, it makes it easier to crack. And let's add here a text. Okay. I think I will make this another slide. Okay. Uh, okay, I think this looks good. Let's make them a little bit more smaller. Okay. So now you know the reasons. All right. And let's continue. And the winner is, let's read it.
NIST announced Kekek as the winner of the SHA-3 cryptographic hash algorithm competition on October 2, 2012, and ended the 5-year competition. Kekek was designed by a team of cryptographers from Belgium and Italy. They are Guido Bertoni, Italy, of ST Microelectronics; Joan Damon, Belgium, of ST Microelectronics; Michael Peters, Belgium, of NXP Semiconductors; and Giles van Osch, Belgium, of ST Microelectronics.
So SHI3, let's look at it.
SHA-3, Secure Hash Algorithm 3, is the latest member of the Secure Hash Algorithm family of standards, released by NIST on August 5, 2015. 4.5. Although part of the same series of standards, SHA-3 is internally different from the MD5-like structure of SHA-1 and SHA-2. Kekik is based on a novel approach called sponge construction. 12. Sponge construction is based on a wide random function or random permutation, and allows inputting, absorbing, in sponge terminology, any amount of data, and outputting, squeezing, any amount of data, while acting as a pseudorandom function with regard to all previous inputs. This leads to great flexibility. NIST does not currently plan to withdraw SHA-2 or remove it from the revised secure hash standard. The purpose of SHA-3 is that it can be directly substituted for SHA-2 in current applications if necessary, and to significantly improve the robustness of NIST's overall hash algorithm toolkit. 13.
So what is NIST, if you wonder? NIST is the National Institute of Standards and Technology. Okay. So SHA-3 has also a different size of bits, as you can see. This is just the algorithm itself. The number of bits still same, or you can set number of bits you want. Of course, when you increase the number of bits, it takes more time to calculate, and it takes more space on the hardware storage. Okay, you can get more idea on it if you want. I will just continue. Okay, there are some algorithms. Okay. I think I will add this lecture here and continue next week from here. Okay, because it is getting overtime. I am going to upload this to the our GitHub. Let's add lecture 3. I'm going to split it as a lecture. So I can have both. Okay, I will upload. I'm ending the lecture here. See you next week. Hopefully, stay safe from coronavirus. And end of lecture.